This is the Lewis diagrams, Lewis structures 3. Lewis structures 2. And this time we're only going to talk about multiple bonds. In the first one we talked about single bonds and how to count valence electrons. But now with this one, we're going to use multiple bonds here. So this time we're going to talk about double and triple bonds specifically, but it should go quickly. And we don't always know if a double bond is going to show up or a triple bond. And so let's take an example here of oxygen O2. And when we go to the table, just to refresh your memory, if we look at oxygen here, you'll see that oxygen is in group 16, but we don't have 16 electrons on the outside of oxygen, we have 6. And so we talked about how they're arranged, but we don't really even worry about that. We just need to know that there are 6 electrons. Okay? So we do have 2 of them though, so that's going to be 2 times 6 gives us 12 electrons that need to be distributed around this oxygen atom. And so you have 2 oxygens, and you also have 2 electrons in the middle. And then Benway's rule for distribution of outer electrons is go away from the center. So we have 12. We start with 2, 4, 6, 8, 10, and 12. Now the problem is that one of the atoms has 8, which is great. 8 is great. So we draw a circle because it's kind of like an 8. There's 8 electrons, but this one does not. This one only has 6 electrons. So we haven't finished. We have to make sure we use 12 electrons, but that each has 8. So what happens is we can say that these 2 electrons, any 2 of these, I guess, but we'll assume 2 gets shared with the other oxygen. And so what that does is results in this arrangement now. Okay? But watch what happens now. Because of that, this oxygen is left with only 4 electrons. It's 2 unshared pairs. And I'll show you why we draw them like that later. Okay? But this is the final structure of oxygen O2. And we don't have to draw the circles anymore. There's 8 electrons around the left one and a total of 8 on the right. The reason we draw the electrons the way we do is because they simply don't want to be near each other. So there's a lot of negative electron charge here. And so the best way to put these electrons far away would be like this. And in nature, that happens to be a 120-degree angle. Okay? So that's why we draw them like that. We could draw them the other way, but this is more accurate of what really happens. Okay? So there's O2, which has a double bond. Let's try another one. This time let's draw with carbon monoxide, carbon with 1 oxygen. And so when we add those, we get 4 for the carbon and then 6. So we have a total of 10 electrons that goes around carbon monoxide. To draw the skeletal structure, you just do that. And then we have to count up to 10 to get rid of all of the electrons. Always put them away from the central position. It just works out better that way. So we now have 2, and we have to get up to 10. So there's 2, 4, 6, 8, 10. Now we have quite an arrangement here because we don't have 8 for either one. If we look here, this has 6 electrons attributed to carbon. And then we have 6 attributed to this one also. And so that can't work because we won't be finished. We did use up 10 electrons, but we need to have octet around each one. So what happens is this. The carbon can share its electrons and still have its total number, 2, 4, 6. That oxygen then will gain, it'll have 2, 4, 6 plus those 2, that'll be 8. But it could also be that the oxygen decides to also share. And so I want you to play with this and come back to it to make sure you understand. But what happens then, here's carbon and oxygen, but because this carbon shared an electron pair, let me put that right there, and oxygen shared an electron pair, and what's left? We didn't change these, so we could say that 2 were left there, and those 2 remain unchanged. Now we still have 10 electrons, but we also have 8 claimed by the carbon, 8 claimed by the oxygen. So that's how we draw the complete structure for the carbon monoxide, CO. All right, let's do another one and see if we can learn a little bit more here. Is there double bonding in chlorine? Let's see what happens here. So we have Cl2, that's 2 times 7, that gives us 14. Okay? You have to remember that, and something's going on with the lighting. There we go. So let's see what happens here with chlorine. We have just a Cl and a Cl. That's 2, and 4, 6, 8, 10, 12, 14. There's no double bonding in chlorine. We're done. It's pretty simple. Okay? But the reason I showed you that is because we don't always know. Right? Let's look at N2. What would we have there? This is 2 times 5 because nitrogen is what we call group 15. Okay? So we draw nitrogen here. We draw the dots. I would get a marker if I were you. Saves you some time. There's 2, 4, 6, 8, 10. And so guess what? That is the same arrangement we had with carbon monoxide. I'm going to show you this time, though, separately. If we did this, right, a little goofy, but 2 there, and then we could do this somewhat incorrectly, but so now the one on the left has 2, 4, 6. The one on the right does have 8, so this one's not complete yet. So then what would happen is that we would need to share once more. And so then you would have 1, 2, 3, a triple bond, and they would be like this. Then you do have a complete octet for both. The one on the left has 8, and the one on the right has 8 also. So that's a pretty quick explanation of multiple bonds, but you'll see in the next video that we're going to add some ideas to that using what is called resonance and ions.